All right, let's dive into a really cool puzzle that popped up online, one of those engineering questions that really makes you scratch your head. It's a paradox that seems to fly in the face of what we know about energy, and it all starts with a little device called a Peltier cooler. So here's the post that kicked this whole thing off. Someone's looking at the specs for one of these coolers, these solid-state gadgets that get cold on one side and hot on the other, and they're just confused. The numbers they're seeing don't seem to match up with the super low efficiency they keep hearing about. And you know what? It's a completely fair question.
Okay, let's just lay out the numbers they're looking at. You put 150 watts of electricity in. In return, the device moves 100 watts of heat out of something. I mean, on the surface, moving 100 watts by using 150 watts of work, that sounds like it's around 66% efficient. So why is everyone saying these things are crazy inefficient, sometimes even less than 10%? And that's the big question, isn't it? If we're putting 150 watts in and it's moving 100 watts of heat, where's that other 50 watts going? Does it just vanish? To figure this out, we gotta pop the hood and see what's really happening inside.
To get to the bottom of this, we need a quick look at how these things even work. See, they're not like your kitchen fridge. There are no compressors, no liquid coolant, no moving parts at all. This is all about pure physics. The secret sauce here is something called the Peltier Effect. And honestly, it's kind of like magic. You run a simple DC current through a special junction of two different materials, and boom, one side gets cold and the other side gets hot. It's not creating cold, it's physically moving heat energy from one spot to another.
And here's what it looks like on the inside. It's so beautifully simple, right? It's just these little cubes of semiconductor material all sandwiched between a couple of ceramic plates. The key takeaway here is that nothing is physically moving, which is the secret to their incredible reliability. So, the main players are these P-type and N-type semiconductors. They're what creates the energy difference for the electrons to do their thing. Then you have the ceramic plates, which are great at letting heat move through them but don't conduct electricity. And finally, the little copper tabs just link them all up in a series. It's an electrical circuit and a thermal pump all rolled into one tiny package.
Okay, so now we know the basics of how it's built, but that still doesn't solve our original mystery. So let's get down to the real heat problem and find the missing piece of this whole energy puzzle.
All right, back to our numbers. The cold side is working exactly like it's supposed to. It's pulling 100 watts of heat energy away from whatever you've stuck it to. Could be a computer chip, a drink, and a cooler, whatever. That part of the math is totally correct. And here it is. This is the big reveal. That 150 watts of electricity you're pumping into the device to make it work, that energy doesn't just disappear. Because of the natural electrical resistance inside those little cubes, all of that input power also gets converted directly into, you guessed it, heat. So this is the absolute key. The hot side of the cooler has a massive job. It doesn't just have to get rid of the 100 watts of heat it moved from the cold side. It also has to get rid of the 150 watts of waste heat that its own operation created. You add those together, and suddenly your hot side has to dissipate a whopping 250 watts of heat. You have to deal with 250 watts of heat just to move 100.
And this is exactly why the word efficiency is so confusing here. It's just not the right way to measure what's happening. For things like heat pumps, engineers have a much better term. As Reddit user Brassica points out so well, we use the coefficient of performance, or COP, and the reason is pretty simple. With some heat pumps, you can actually move more heat energy than the electrical energy you put in. That would give you an efficiency of over 100%, and that just kind of breaks our brains. COP avoids all that confusion. The formula is super simple. It's just the heat you successfully moved from the cold side divided by the electrical power you had to put in to get the job done. For our original example, that's 100 watts moved divided by 150 watts in, which gives us a COP of about 0.67. But that number of 0.67 doesn't mean much without context, so let's put it next to something we all know, like a window air conditioner. A pretty standard AC unit might use 1,000 watts of power to move 3,000 watts of heat out of your room. That's a COP of 3.0. When you compare our Peltier's 0.67 to a 3.0, well, now you see why we don't air condition our homes with these things. So if they're that inefficient, why on earth do we even use them? Well, it turns out that for some very specific jobs, their unique skills make them not just the best option, but the only option. I mean, look at these advantages. They're silent, incredibly reliable because there's nothing to break, and they're tiny.
But their real superpowers are that they can cool things to below the surrounding room temperature, and they can hold a specific temperature with unbelievable precision. We're talking within 1/100th of a degree. Plus, you can just reverse the electricity and it instantly becomes a heat.
This is their sweet spot, high-end scientific and medical equipment. Things like lab instruments that need to keep a biological sample at an exact temperature no matter what. For jobs like that, a low COP is a tiny price to pay for that level of control.
But you'll also see them in more common places, like those little portable coolers you plug into your car's 12-volt outlet, some office water dispensers, or for spot cooling a really hot computer chip where a big, clunky cooling system just wouldn't fit.
Okay, but hold on, there's one last fascinating twist to this story. This whole process, it can be run in reverse. Instead of putting electricity in to create a temperature difference, you can use a temperature difference to create electricity.
This is called the Seebeck effect. If you heat one side of the device while keeping the other side cool, those same little semiconductor blocks will start to generate a voltage. Your heat pump suddenly becomes a tiny power generator.
And this, of course, leads to another fantastic question from the forum. If it's hot outside and cool inside my house, why not just line my walls with these things and generate free energy from that temperature difference? It sounds like an amazing idea.
But as user Ragnorby points out, the problem is that same old low efficiency. For the device to make power, heat has to flow through it. This basically turns your wall into a big thermal leak. You'd let in way more heat than you could ever hope to convert into useful electricity, forcing your AC to work way harder. So the bottom line is, good insulation will always save you more money.
So there you have it. The paradox is solved. It's not about traditional efficiency. It's about managing the total heat you have to get rid of. And while Peltier coolers aren't for every job, their unique strengths, being totally silent, solid state, and incredibly precise, have earned them a crucial place in our high-tech world. It just makes you wonder, where else could this quiet, reliable little technology pop up next?